Welcome to the Talking the Talk podcast, where we'll be exploring items of automotive technology and their journey into mass production. I'm Kevin Reid, the founder of Ireland Made, where we celebrate stories of Irish transport past and present, and this is our podcast. I'm delighted to welcome my co-host, Automotive Engineering Consultant Mike Keane. Mike's consultancy delivers bespoke and sustainable transport solutions, and previously Mike has led vehicle development programs for Ford, Williams Formula One Advanced Engineering, Nissan, Jaguar, Land Rover, and Aston Martin. Mike has also worked on projects as diverse as hybrid supercars to off-road electric vehicles. But what is most impressive for me, Mike worked on the James Bond movie Spectre, and he worked on the baddies car, the Jaguar CX-75. In each episode, we're going to be examining vehicles that range from the 1921 German Rumpler right up to what Tesla and Lucid are doing today. On our last episode, we talked about fuel systems in cars and trucks. And today, in episode 8, we're exploring automotive safety systems. So, Mike, where do we begin?
Hi, Kevin. Yeah, safety systems, they're an intrinsic part of how modern cars are designed and developed. And you can break safety systems into two different types. We call them active, or sometimes called primary systems, and passive, or sometimes called secondary systems. So in recent years, active systems have actually taken quite a lot of prominence. So the active systems are the systems that prevent or try to prevent an accident from happening. So if you think of, on a modern car, you have things like adaptive cruise control, lane assistance, collision avoidance, pedestrian detection, all these sort of things. So they're actively trying to stop the accident from happening. Today, we're going to talk about passive systems or secondary safety. So these are the systems that are built into the vehicle to make the vehicle safer when an accident does actually happen.
Right. Excellent. So where does our story start?
Well, normally, Kevin, on the Ireland Made website, you like to celebrate stories of Irish transport history, right? Well, today, unfortunately, we do have Irish links, but they're not ones that we can celebrate. So the first fatality that was recorded to have been caused by a car was an Irish woman. So a woman called Mary Ward in 1869. So she was a scientist and a writer, and that was a time when universities didn't actually accept women. So as a result, she was a pretty prominent figure. And because she was prominent, her death was widely publicized. So her cousins had built a steam car. And unfortunately, on a day where they were taking this car for a test drive, she fell off the car and she was crushed under its wheels. So an unfortunate.
That's an unfortunate Irish connection.
It is. And in a weird coincidence, again, an unfortunate coincidence, we have another similar Irish link, which is the first pedestrian to have ever been killed by a car was another Irish lady, a woman called Bridget Driscoll, and she was killed in London crossing the road. So that was a time when cars were, still weren't very common. But the thing about her death was it actually happened 2 weeks after the British government had increased the speed limit in London.
Wow. So both unfortunate deaths. So when did the government start placing legislation on car design?
Well, so the earliest sort of legislative efforts, they were all concentrated on the driving environment rather than the cars themselves. So things like traffic lights and road signage or even pedestrian crossings. And sort of the early stages, the safety of the cars, it was left up to the manufacturers. Some manufacturers considered some safety systems, but it was still quite ad hoc. And sometimes, they were quite reluctant about it as well.
All right. So where did the reluctance come from?
Well, designing cars is expensive, right? And designing safety systems is expensive. So if the legislation isn't requiring a safety system to be incorporated, then the car companies, were reluctant because, it was expensive and therefore they paid sort of little or sort of, a token regard to safety. It's sort of an indication of society at the time as well and the expectations of society. So if you come right up into the mid-50s, so in the mid-50s, Ford launched what they called the lifeguard system. Now, in terms of safety in vehicles, it was actually class leading. So it was an option on the cars. The cars could have an option of front and rear seat belts. In fact, the first cars with rear seat belts. And they had things like safety glass in the rear view mirror. And even the steering wheel was deep dish and the spokes were flexible, so it would move out of the way. But yet Henry Ford himself he's quoted as saying that these systems sell safety, whereas Chevrolet are selling cars. So that kind of gives you an indication of the thinking of Ford himself. But as I said, it's also a sociological aspect, because the buying public didn't value the cars. That's why Chevrolet were selling cars and Ford weren't. So rather, they didn't value these systems. And then also the legislation didn't ask it of the car companies as well.
Right. So some car companies then would have introduced their own systems independently. And I'm thinking straight away of Volvo. I'm also bearing in mind my 1965 Volvo Amazon, which I think is the first car to be fitted with seatbelts. And it's like this ginormous carabiner that you sort of, like something you climb a mountain with, and you clunk it into a steel loop that's mounted on the floor between the two passengers. So was that the first car with safety seatbelts? No,
it wasn't. So Volvo were the first company to really make a sales feature out of safety. So for instance, in 1944 on the PV, they introduced laminated glass, but actually it wasn't the first car with seatbelts. So the very first car with seatbelts was an option on a car in 49, and it was a Nash 600. And then sort of in the 50s, Ford had that lifeguard system we talked about. And actually the first car that had seatbelts as standard was the other Swedish car company, Saab. So in 1958, they put seatbelts on their 93 model. But Volvo made two very big contributions to safety in those early days. So they weren't the first with seatbelts, but they did invent the 3-point seatbelt. So the seatbelt that went over the lap and over the shoulder. Up until that point, seatbelts were lap belts only. And although they were better than not having a belt, they actually cause horrific injuries because of the lap pulling across the center of the torso. And then the 3-point seatbelt that Volvo invented, that was over the shoulder and held the torso in position. And that was one big contribution that they made, but they made another big contribution as well.
And what was their second contribution?
So the second contribution, and I think it's actually bigger than the invention in the first place, is that they made the patent open. And that meant that other car companies could freely copy the invention. And, I think that decision to focus on the benefit of general safety rather than the commercial benefit for Volvo themselves, I think that's one of the most important contributions ever to car safety.
Very interesting. So I'm thinking then after seatbelts, the next obvious step forward is airbags.
Yeah, airbags started to come on shortly after that. So the Oldsmobile Tornado in 73, that was the first car fitted with an airbag. And then we see more and more airbags right up until then. In 1987, the Porsche 944 Turbo was the first car with driver and passenger airbags as standard. And at this point, there's still options. And then in late 90s, so in 1999, they became mandatory in the US.
So now we're reaching the stage in automotive development where legislation is mandating safety systems.
Yeah. So in the mid 60s, that's when we start to see sort of government agencies really start to make their presence felt with legislation. So in the 60s, in the US and Europe and Japan, there's sort of a growing societal awareness and a reaction to the road deaths. So in fact, in Japan, they call them the traffic wars. So at first, the government sort of mandated specific features, like they would say that a car has to have seatbelts, or, like we said later on, had to have airbags. And at the same time, sort of in the 60s, legislative bodies were being created looking specifically at safety. So in the US, for instance, there's the NHTSA, which is the National Highway Transport Safety Administration. But even at first...
Sorry, Mike, to cut across you. I think it's the National Highway Traffic Safety Administration.
Sorry, yeah, traffic.
So sorry to be pedantic.
No, you're absolutely right. But even at first, sort of these legislative bodies, that they were quite weak, and the car companies were able to influence the regulations. And then in that 60s period, late 60s and 70s, there were two particular events in the US that really shifted public opinion, and as a result, they created political pressure. And that ultimately is what caused the governments and the legislative bodies to start, being sharper in how they tackled these problems.
Okay, so let's explore both of those. What were they?
So the first one was in 1965. So Ralph Nader, you might recognize him because he later on became a presidential candidate in the US. So he wrote a book called Unsafe at Any Speed. And in that book, he was very critical of the cost-benefit analysis, which is the method the car industry would often use for deciding the safety of their vehicles. So, and then, you can think of like that Henry Ford comment on, we're selling safety, but there's Chevrolet are selling cars, right? So Nader, he famously drew attention to the Chevrolet Corvair, and the Chevrolet Corvair had a propensity at sort of high speed to have a dangerous level of oversteer. So, if we look at technically why was the Corvair in particular prone to this? So it's a combination of design selection and also management choices. So the Corvair had what's called a swing axle suspension. Pretty common at the time. A number of cars had a swing axle suspension. Volkswagen Beetle, Triumph Hurler, Spitfire, even the Mercedes Gullwing, they all have a swing axle suspension. Now, in most cars, when the wheels rise and fall as the car travels over bumps, the suspension is designed in such a way that it keeps the tire perpendicular or as close to perpendicular to the ground to maximize the grip. A swing axle suspension, the drive shaft and therefore the wheel, it pivots from a center point in the car. So it just rotates up into the car or down underneath the car. So that's the first thing. And then the second thing is that, when you drive any car, when you go around a corner, the body of the car leans. So if you drive through a right-hand corner, the body of the car leans to the left, and you have a sort of this feeling of leaning down towards the ground, towards the left-hand side. And that's because the center of gravity of the car, it's rotating around an imaginary point called a roll center. So the roll center is kind of this imaginary center pivot for the whole car. With a swing axle, because of the peculiarities of the geometry, this imaginary roll center, it's located above the center of gravity. So instead of the car leaning down towards the ground, it has a strange effect where when the car corners, the body acts almost like a pendulum and it lifts the car up. So if you go around a right-hand corner, the left-hand side of the car lifts up.
So in effect, then the body lifts up and the wheels tuck in underneath.
Right. So you had this combination, exactly. This really, really not good combination of things happening. And then on the Corvair in particular, that phenomenon, it's combined with the fact that the Corvair was rear-ended and had a big flat six air-cooled engine at the rear. So there's a lot of weight hanging over the rear of the car. And all of those combined to mean that at high speed, it could have snap oversteer, so very sudden oversteer, so dangerously so. And then the problem then was that rather than fixing the suspension geometry, which would have been costly, Chevrolet's response was to specify that the rear tires had a very low tire pressure and the front tires had a high tire pressure. So a very mismatched tire pressure between the front and the rear. It's sort of a way to try and falsely generate some grip at the rear. But of course, a lot of people didn't know that. Owners didn't know that, wouldn't expect that, and would have just naturally put more or less the same amount of pressure into all tires. And then therefore there was sort of disastrous consequences then as a result.
My God, what a strange engineering solution. But you're absolutely right. People had just put the same tire pressure in all four cars and then, right, as you say, go on to having a car crash. So what was the second event? What was the other event?
So the other one was, so that was in Ralph Nader's book. The other one was separately to Nader's book. Again, it was a cost-benefit analysis. And this one is also quite famous. So it was the Ford Pinto of 1970. So the Pinto was a small car in the US, what they would call a subcompact. Wasn't a particularly bad car, wasn't a particularly unusual package. So it was designed with the same package layout that was pretty common for most cars at the time. So the fuel tank was mounted right at the rearmost point of the car.
Yeah, that's exactly the same in my Amazon, the fuel tanks in the boot.
Yeah, that's right. Yeah, it was pretty common at the time. So in the Pinto, the fuel tank was placed right behind the rear axle. But because it was a small car, sort of a hatchback size, as we would call it in Europe, there was very little structure rear of the fuel tank. And what structure was there was actually not very strong. So there was very little impact resistance. And that caused quite a number of rear end accidents whereby the Pinto would go on fire. And unfortunately, it caused fatalities. Now, the serious underlying problem here was that the industry and the regulatory bodies, they worked together using a sort of a cost-benefit analysis to determine what legislation was appropriate for safety systems in cars. So in 1976, Ford's safety engineering team, they produced a report for the NHTSA that highlighted.
So sorry to stop you there, Mike. I actually think it was 1973.
Sorry, 73. Thanks. Yep.
Yeah. Sorry.
That's right. Yeah. So they created a report that highlighted that the cost of re-engineering the safety systems, the fuel systems of all of the vehicles of all of the manufacturers in the US would be over $135 million. Whereas the compensation from all of those manufacturers to victims of injury and death would be less than half of that. And the implication being that it was more expensive to make the change to the car than to allow the cars to remain in the state that they were in. Now that report, that was picked up by the prosecution team in the litigation case against the Ford Pinto. And the courts weighed in very heavily against Ford. And the result of that case and sort of the public response to that, it changed the industry's approach. And it also changed that sort of slightly cozy relationship that the car companies had with the regulatory bodies.
So the test became more stringent and the coziness was over. Yeah,
that's right. So what started happening then is the regulatory bodies started carrying out independent crash testing. And then in the 90s, the regulatory bodies started giving star ratings, so sort of based on a 5-star rating. And as the public became more aware of these ratings and they started to respond to them, then the ratings themselves started to have more authority. So to give you one example, so the Euro NCAP, so the NCAP is the new car assessment program, and that's the program that you would see, in car ads. Car manufacturers are happy to say it's a 4 or 5-star rating. So that was launched in 1996. In 1998, the Rover 100, the car that had been the Metro, it was given a 1-star rating. And sales immediately plummeted for the car to the extent where Rover stopped the production and the car production was cancelled after almost 18 years.
So the authority that the public now had, they were reflected in their buying responses. Excellent. That's right. So what then is involved in crash testing? Well,
crash barrier testing, that's actually been going on since the 1930s. So GM first started carrying out their own internal crash barrier testing in 1934. And then, as I said, with that independent testing in the 90s, it ramped up very significantly. So in crash barrier testing, the car is pushed at speed against the barrier to understand how it can withstand the impact. And nowadays, there are multiple different types of tests. So you've got different types of barriers or obstacles. The cars impact at different speeds. And the barriers and obstacles impacted the cars in different locations on the car and even at different angles as well.
So this is when we see a large stationary object like a wall and a car being towed at speed and then terribly deforming when it impacts, like the car almost pancaking.
Yeah, so you see these really aggressive impacts. But it's funny though, you say terribly deforming. So actually in a modern car, when you see the car being destroyed, that's not necessarily a bad thing. So the vehicle engineers are balancing two different aspects. So one is called G-pulse and the other is called intrusion. So G-pulse is the impact energy. And what the engineers are trying to do is limit the amount of impact energy that gets transferred into the occupants so that you have less of that effect where the occupant is thrown around inside the vehicle. And in order to manage the G-pulse, sections of the vehicle are designed so that they'll collapse in a very controlled manner. So it's very aggressive, it happens quickly, but it's actually controlled. And these are called crumpled zones. You recognize that phrase?
Yes.
So crumpled zones, what they do is they dissipate the impact energy so that energy is not transferred to the occupant. But at the same time, the occupant area must stay rigid. So the balance is have the vehicle collapse in a certain way, but a limited intrusion into the occupant. So that occupant area must stay nice and rigid and safe for the occupants.
So that would have to be fairly cleverly balanced. So let's explore, how would that be balanced?
Right. So if you look at the structure of a car, so you think kind of front to rear, so think about a front end impact or a rear end impact. So typically what happens in the car is there's a deformable section at the front and a deformable section at the rear, and then a very rigid sort of safety cell in the center where the occupants are. Interestingly, the first car with that approach was in 1959. It was a Mercedes-Benz 220. And then that's really common today. And then so that's for front and rear. For side impact, it's a similar approach, but as you'd imagine, there's less material, there's less vehicle to work with coming in from the side. So for a side impact, the emphasis is much more on just stopping the intrusion into the cabin. So going back to Volvo again, so in 1991, Volvo launched the SIPS, the Side Impact Protection System. You might have heard of that phrase. They put it on the 700 and the 900. So the SIPS system has very strong beams inside the door. And what that does is it transfers that impact energy from the door into the pillars of the vehicle through the hinges and through the latches.
Okay, so all that impact energy, that's all determined in testing. They can measure that in testing.
Yeah, so it's in testing, but it's not actually all in physical testing. So nowadays, the structural engineers and the safety engineers, they carry out digital testing using very powerful computer simulation tools called finite element analysis. So in an impact, what they do is they look at all of the components of the car. So in an impact, some of those components will deform and shatter, and some will stay as solid pieces and they'll just move around the car. So the engineers run multiple crash simulations and they digitally look at which components are deforming and how they deform and which components move. And then they sort of play a complicated design game where they try to get all of those pieces to fit together, sort of like a complicated version of Tetris, where as the car collapses, the deformed pieces absorb the energy and the solid pieces move into the right place in a very controlled manner.
So with all of that going on, I would imagine that would change the design layout of a car.
It does. It has a lot of implications on, particularly like in the engine bay, you see a lot of work. So, I'm very lucky, Kevin, that I don't come from that era of the era of the Ford Pinto, or that way of thinking. And so nowadays, car companies set very stringent design safety rules. So internally, they're very stringent for what's acceptable. So if I give you an example, I was an integration engineer with Ford on their 1 litre EcoBoost engine. And part of the integration role is to ensure that the engine is in compliance with Ford's own safety rules. And one example, which is very typical of what car companies need to do. So very early in that program, when the engine was still being designed, the cylinder head was turned through 180 degrees. And that was done to move the turbocharger onto the front face of the engine. And that was to ensure that there was no intrusion into the cabin through the dash panel wall.
That's fascinating. That's the sort of clever stuff I'd never think of in a million years, but it makes so much sense. That's brilliant. Any other examples?
Yeah, lots. So safety engineering, it's a key area, and I've dealt with it, in quite a lot of times, quite a lot of ways over the years, either as the owner of systems, like, the owner of the fuel system, or sort of, in roles where I've had whole vehicle responsibility. So to give you one example, when I was working for Williams Advanced Engineering, I was a technical lead on a pre-production prototype concept car called a Nissan Blade Glider. And that was to be an electric sports car. Now, I talked a moment ago about all of the different crash testing and different types of obstacles. One of them is called a side pole impact test. And that is, literally, as it says, it's a pole that the car impacts side on.
That would mean that the car is basically wrapping itself around something.
Exactly. Yeah, exactly. Okay. So you think of a telephone pole, right, or electricity pole, that sort of pole. So that's a particularly difficult test for EVs because typically the battery is floor mounted in an EV and it's quite wide. So there's very little structure between the outside of the vehicle and a wall of the battery. And batteries, there's very strict rules as to, how much deformation a battery can handle. So on that Nissan Blade Glider program, so Nissan themselves, but again, as with all car companies, they have very stringent design rules on what levels of G-pulse are allowed, and even the time duration for that G-pulse. So it's not just enough to look at how many Gs, but actually over what period as well. And also very strict rules on the level of cabin intrusion that's allowed. And all of that meant that in that program, the layout of the battery, the position of the passengers, the structure of the sills, the structure of the doors, we had to go through multiple loops to try and get that vehicle to digitally pass those crash simulations.
So because of their positioning, batteries in electric cars are going to be a difficult design task from a safety perspective.
Yeah, they have some specific things. Now, by and large, actually, EV batteries present more or less the same safety challenges as a fuel tank, let's say as a petrol fuel tank. So if you think about, and we talked about fuel systems in the last episode, so the battery or the fuel tank, they have to be engineered so that they're not breached or they're not pierced at an impact, so that they can withstand the fire around them. You remember the grass fire test we talked about in the fuel systems chat. And they also have to be able to withstand overpressurization from inside. So car companies, they have strict rules about what's allowed. They also have rules that the battery or the fuel tank, they can't be stressed members. So that means that any flexing of the car body can't impart stress loading into the battery or into the fuel tank.
Wow. So there's very specific safety challenges to an EV. And I'm thinking of that was thermal runaway. So that's when an electric car has gone on fire. And the only way to absolutely ensure that the fire is out is to take the car and immerse it into a skip filled with water.
Yeah, so actually that does happen. That's in the very extreme example. So thermal runaway is a situation where the battery internally has gone on fire, and then it self-propagates. So the heat of the fire creates more thermal issues in the cells, and therefore propagates more and more fire. And in that scenario, fire responders or fire brigades, sometimes what they have to do is actually put the car into a vat of water in order to put it out.
Wow.
The biggest thing probably in safety engineering for vehicles, for EVs, is high voltage protection. So EVs operate at very high volts, so anywhere between 150 and 800 volts in the latest cars. And the volume car companies, they engineer those batteries to very high standards. So the batteries, and indeed all of the high voltage installations, they have to cope with a series of aggressive abuse cases. So they have chemical, environmental, mechanical, electrical abuse cases, as we call them. So it's one of the areas that, volume car companies are very good at. The big legacy players are good at, and they engineer to a very high standard. And there's legislation that pushes them to meet those standards. It's an area that I have concerns about actually a little bit when we talk about the rise of sort of the small and the independent EV companies. Now, don't get me wrong, I'm an enthusiastic supporter of small companies. I currently work with a number of small EV companies. Small companies often are able to produce niche products that are just not viable for the mass manufacturer. So really big support of them. But at the same time, I also know that the testing criteria that's asked of the small volume manufacturers, it's not as stringent as those of the high volume manufacturers. So when I see a small EV company now, I always pay a lot of attention to the certification standards that they can genuinely achieve, or that they have genuinely achieved with their designs.
So that's to ensure that they're keeping the cars safe for the drivers, for the occupants of their cars in an accident.
Yep, for the occupants, but also for pedestrians and also for first responders. Right? So if you think about it, that in the case of an accident, the first responders, the fire brigade, the ambulance, the police, they're the first people to come into the damaged car. And the risk in those accidents is that there's what we would say a high voltage leak. So there's high voltage somewhere in the car that they don't expect.
Now, just after realizing it's a very narrow question I just asked you. So, of course, there's going to be people in the car, people around the car, and people responding to the car. So how do the big companies deal with this? Well,
so specifically looking at the first responders, the big companies pay a lot of attention in this area. To give you two examples, so in Teslas have a specific loop of electrical cable that the first responders know about. And when a Tesla is in a serious accident, the first responders cut that loop of cable, and that disconnects the entire voltage system. So it makes the voltage system go dead, nice and safe. And then I'll give you another solution, and I think this is a really brilliant solution. So this is on the Renault Zoe. So the Renault Zoe is a small family hatchback EV. So under the carpet, under the passenger seat in the Renault Zoe, there's an access panel to get into what's called the main safety disconnect switch. Now, the MSD is a switch that's on all batteries. And that's a switch that when you disconnect that, it disconnects all of the voltage and it makes the battery no longer live. Now, that panel is underneath the carpet, but obviously there has to be good access to it, but it also has to be locked and it has to be secure so that you can't get interference from occupants. You don't want kids able to stick their finger down there.
Last thing you want is the child to be turning off the key.
Absolutely. So it has to be locked, it has to be secure, but at the same time, the first responders have to be able to access it easily and quickly. So the solution that Renault came up with, I think, is brilliant. The key that you need to open that panel is the same key that you use to open a fire hydrant. So it's a key that, regular people, you and I won't have one of those hanging around. We won't have one of those in the car, but it's a key that it's on all fire engines, and therefore first responders will always have one to hand. I think that's a brilliant solution.
Thank you, Mike. Very informative discussion today. I can envisage that safe and legal is where you're going to be working on with your clients for the next number of years. Please join us next time where Mike and I will be exploring body structures. Bye for now. Thank you for joining us today on the Talking the Talk podcast. My thanks to Mike Keane, and you can check out his consultancy on mikekeane.ie. Then check out irelandmade.ie to view our back catalogue of videos celebrating stories of Irish transport, past and present. We look forward to welcoming you onto our next episode where we further explore the origins of automotive technology. You can find us on YouTube or Spotify or wherever you get your podcasts. Please subscribe and tell your friends. Bye for now.